Welcome back to Course 1.0, 3D Implant Mastery. In Lesson 1, we established that the bone is the foundation, determining 90% of implant success. Today, we focus on the other 10%, the device itself, the dental implant. Many patients ask for the best brand. We, as professionals, know that brand loyalty is secondary to understanding design philosophy and material science. An implant is a mechanical anchor in a biological environment. Understanding its components is critical for achieving optimal primary stability and long-term success. This lesson will help you look beyond the marketing and evaluate the device based on engineering and biology. 3D focus. We are moving from the biological constraints revealed by CBCT to the mechanical solutions offered by engineering. The choices made here directly mitigate the risks we identified in Lesson 1. 1. The material deep dive, titanium grades and beyond. Let's start with materials. The vast majority of implants are made of titanium, but not all titanium is equal. We primarily differentiate between pure titanium, grade 4, and titanium alloy, grade 5, or T6 alpha 4V. Grade 4 offers excellent biocompatibility, but grade 5, alloyed with aluminum and vanadium, is significantly stronger, up to 40% stronger. This higher strength is crucial for smaller diameter implants or those supporting complex restorations. Visual. Show the microscopic difference in crystal structure. This strength difference becomes critical in high-stress zones, such as posterior molar replacements or narrow ridges. Grade 5 allows for the necessary resilience against fatigue fracture over decades of chewing. Visual. Show finite element analysis simulation of stress on a grade 4 versus grade 5 implant. We must also consider emerging materials. Zirconia implants have gained traction due to their aesthetic white color and metal-free properties crucial for patients with thin biotypes or allergies. While highly aesthetic, zirconia is less forgiving mechanically. It lacks ductility and is highly susceptible to low-temperature degradation or aging. Visual. Contrast the mechanical properties. Titanium bends, zirconia cracks. It is typically used as a single-piece unit, which limits restorative flexibility and means they are not suitable for all loading conditions, requiring a distinct surgical and loading protocol. The material choice dictates the limits of the screw, the abutment, and the expected long-term fatigue resistance. 2. Macro design, body shape, and thread geometry. Next, let's examine the macro design, the overall geometry. The two primary body shapes are parallel-walled and tapered or conical. Parallel-walled implants were the standard for many years, relying on precise bone preparation. Tapered implants, however, mimic the shape of a natural tooth root. They're excellent for achieving high primary stability in softer bone types, D3 and D4, through self-condensing properties, which is vital for immediate loading protocols. Visual. Show tapered implant self-tapping into D4 bone. The thread design is equally critical. Threads are not just for insertion, they are the primary mechanism for transferring occlusal load to the bone. We see variations like the V-thread, common, efficient for self-tapping, and the square thread, with greater surface area, theoretically better load distribution, but harder insertion. Aggressive, deep threads are designed for self-tapping and faster insertion, but risk overheating dense bone, D1. Compression threads are wider and designed to engage the cortical bone, improving stability but requiring extremely careful drilling. The macro design is the surgeon's tool to overcome challenging bone architecture revealed in our CBCT planning. Furthermore, the implant neck design plays a crucial role in managing crestal bone loss. Some implants feature microthreads on the neck to better distribute stress in the cortical bone, while others use a smooth, polished neck, relying on soft tissue attachment. The choice here reflects different philosophies on how to manage the biological width and prevent the dreaded saw surging, or horizontal bone loss.
3. Microdesign, surface treatment, and osseointegration. The true magic happens at the micro level, the surface and the connection. Surface treatment is paramount for osseointegration. A smooth, machined surface prevents bone integration. Modern implants feature treated surfaces, usually involving grit blasting, SA, followed by acid etching, SLA, or similar. Visual, microscopic view of a porous, acid-etched surface. This micro-roughness increases the surface area for osteoblasts to adhere to, speeding up the healing process. Newer surfaces often incorporate hydrophilicity, affinity for water or blood, which theoretically attracts clotting factors and cells more rapidly, potentially accelerating healing time. Visual, show a drop of water spreading rapidly on a hydrophilic surface. The surface is the first point of contact between the mechanic and the biologic. It dictates the rate of healing. 4. Implant-abutment connection, the weak link. Now consider the implant-abutment connection. This is the weak link susceptible to bacterial leakage and micromovement, leading directly to peri-implantitis. Systems use three main types. External hex, the original, simple but the junction is wide and prone to micromovement, leading to screw loosening and crestal bone loss over time. Internal hex, or octa. It offers better stability than the external hex, partially seating the abutment inside the implant, and conical Morse taper. This connection relies on friction. Visual, show the tight, sealed fit of a Morse taper connection. It creates a cold weld seal, minimizing the microgap where bacteria can accumulate, reducing the risk of peri-implantitis, and preventing rotational movement. This biomechanical stability is essential for maintaining a healthy soft tissue barrier, and is now the gold standard for long-term health. The absence of a microgap is the single most important factor for reducing the late-stage complications of implantology. 5. Key concept, platform switching, and clinical application. Finally, let's define one of the most significant concepts in modern implantology. Platform switching. In a standard connection, the abutment diameter matches the implant diameter. In platform switching, the abutment is intentionally narrower than the shoulder of the implant. Visual, comparison diagram of standard versus platform switched. This moves the junction, the microgap, inward, away from the crestal bone. Biologically, this encourages the soft tissue to grow inward, creating a protective cushion and reducing the inflammatory response, thereby preserving the critical crestal bone level, the primary indicator of long-term implant health. The clinical impact is dramatic. Studies consistently show significantly less crestal bone loss around platform-switched implants compared to conventional designs, making it essential for aesthetic zones where bone volume is already limited. Every student must understand this principle for modern treatment planning. Conclusion. To summarize Lesson 2, choosing an implant is a highly engineered decision. You must select the right tool for the job. Do you need grade 5 strength for a narrow posterior space? Do you need a tapered macro design for immediate stability in soft bone? Do you require the hermetic seal of a Morse taper connection to reduce peri-implantitis risk? Your knowledge of these design parameters combined with the anatomical data from your CBCT, Lesson 1, is what separates a technician from a master clinician. The bone is the foundation, but the right device chosen with precision ensures the structure lasts. Join us next time for Lesson 3, Osseointegration Biological Process Unlocked, where we dive into the cellular mechanics of bone fusion and how the surface treatments we discussed today dictate the speed of healing. Subscribe to Dental Vision 3D.